Okay guys, welcome back to another video. Today we will take a look at Theorem 2.4.6, which state that let a and b be integers such that a is not 0 or b is not 0 and x be integers. Then the greatest common divisor of ab equal to the greatest common divisor of a b plus ax and equal to greatest common divisor of a plus bx b. It's like you can add the second number by a times integers, and you can add the first number by the second number multiplying another integers. For example, you may have the greatest common divisor of 12 and 27, and we know that it is 3. And it can be written as, we start with the first number, which is 12 and 27 plus 12x. In this case, your x can be any integer you might choose. You may choose 51. Okay. Another example, you may add the first number. So for this case, if you have the same greatest common divisor, which is 3, and you may add 12 by another number, in this case it's going to be the second number, which is 27 times, let's use the negative one, let's say minus 99, and the second number, which is 27. Okay. Another example, you may have 5 and 15. The greatest common divisor is 5, and you can add the second number by the first number multiplying any number. So you may have 5, 15 plus 5 times minus 10. Okay. Or another case, you may have 5, the greatest common divisor of 5, and 15, which is 5. Then it turns out to be 5 plus the second number, which is 15. It might multiply by, let's say, 7. Okay, and the second number remain the same, which is 15. Okay, so this is how to use Theorem 2.4.6. Let's prove this theorem. For this one, we are going to use properties of divisibilities, in which I mentioned in Theorem 2.3.1, especially property 5, property 6, and property 8. Okay, and we will use theorem of the greatest common divisor of a and b, which is ax plus by for some integers x and y. Now let's get started. So we gotta let a and b be integers such that a is not 0 or b is not 0, and x is any integers. And we want to show that the greatest common divisor of a and b equal to the greatest common divisor of a and b plus ax. Alright, we want to show this one. And what we can do next, the thing that we have to do is to let d to be the greatest common divisor of a and b, and let g to be greatest common divisor of a, b plus ax. Okay, and what's the next thing that we have to do? We're going to use Theorem 2.4.1 Alright? Which state that the greatest common divisor of AB equal to AX plus BY. So by theorem, I gotta write by theorem 2.4.1, their x's, okay, integers u, v, and m, n, such that d equal to ab, which is au plus bv. And what is g? G is the greatest common divisor of a, b, ax equal to am plus b plus ax n. Okay, I want to rewrite this greatest common divisor into, it's like I want to let a to be next to each other. So we gonna have am plus bn plus axn, which is, so we gotta let this a to be next to each other. So what do we have? Okay, let me move this one to the left side a bit. So we gotta have am plus axn, okay, plus bn, which is a times m plus xn plus bn. Okay, so that's what we want right now. So now let's consider the greatest common divisor of a and b. So since the greatest common divisor of a and b, sorry, d is equal to the greatest common divisor of a and b. So what do we have? So we gotta have d divide ab and d divide b, right? So what do we have next? So by theorem, once we have d divide both number, we want to use this property, which is in theorem 2.3.1. If you have a divide b and a divide c, then a will divide bx plus cy, where c and y are any integers. So what we have right here is to use theorem 2.3.1 number 8. So what do we have? We gotta have d divide a. Let's use x1 plus bx2 for every integers x1, x2. Okay, what can we do next? The next thing that we are going to do is to take a look at our g. Why? Because our g is this term, and m plus nx and n are integers. So I gotta write since m plus xn and n are integers. Okay, so what do we have? So we can have we can have d divide what? Divide a times m plus xn plus b n. And this term right here is g, right? Okay, this is g. Okay, hence d divide g. Okay, d divide g, that's what we have. And the next thing we have to do is to take a look at the greatest common divisor of a and b plus ax. So since since G is equal to the greatest common divisor of a, b plus ax. So what do we have? We're gonna have G divide a and G divide b plus ax. Alright. So what can we do next? The next thing we have to do is to take a look at G divide a. Why? Because it's obvious that G divide ax. Okay, so since G divide a, it's obvious that G divide ax, right? You just multiply a by another number, so G will divide ax. Now, if G divide one of the term of the sum, G will divide another sum. That means that we have to use another property of divisibility. So since G divide ax and G divide b plus ax, so what do we have? We're gonna have G divide b. Okay, this is by Theorem 2.3.1, which is the one right here. Okay, so if a divide the sum of two numbers a and b, a plus c, and a divide b, then a divide c. Alright, so what we have right here is by Theorem 2.3.1 property 5, okay, we're gonna have a divide g. Now we have G divide a and G divide b. What do we have? So since G divide a and G divide b, so what do we have next? So by theorem, so by this property again, okay, so when G divide both a and b, Theorem 2.3.1 property number 8 implies that G divide a, let's use y1 plus by2 for all or for every integers y1, y2. Alright, so that's what we have right here. Okay, and then take a look at our G, or our D here. D, which is the greatest common divisor of AB, which is AU plus BV. So since U and V are integers, so what do we have here? So we gotta have G divide AU plus BV. Okay, and hence this term right here is D, right? It is D, so we're gonna have G divide D. Okay, G divide D. So that's what we have right here. Since D divide G and G divide D, what do we have? Okay, since D divide G and G divide D, so D will be G, right? And therefore the greatest common divisor AB equal to a, b plus ax. Okay, this is what we have right here. And then what do we want to do next? We get to show that the greatest common divisor of AB equal to the greatest common divisor of A plus BX and B. Okay, let's prove this. So we have to show that the greatest common divisor of AB equal to A plus BX and B. Okay, so add the first number by BX. So let's prove this one. Let's prove this. Again, the step will be the same. Actually, the way to prove is very similar. So we're gonna let D to be the greatest common divisor of AB, and let's use H to be greatest common divisor of A plus BX and B. And then by theorem, which theorem 2.4.1. So if you have the greatest common divisor, you can written as the sum of the number inside here, right? Inside the greatest common divisor. So there exists. Let's use S, T, J, and K. Okay? Such that D equal to AB, which is AS plus BT. Okay? And what next? And the greatest common divisor of A plus BX B equal to what? A plus BX J plus BK. Okay? Then I want to write this term to be, I want B to be next to each other. So what do we have here? We can have AJ plus BXJ plus BK, which is AJ plus what? B times X. Okay, give me a second. X J plus K. Okay, let's continue. So what do we have to do next? The next thing we have to do is to try to show that D divide H. Okay, try to show that D divide X. So we want to start with, since D is the greatest common divisor of A and B. So what do we have? D divide A and D divide B. Okay, so by theorem 2.3.1, which is, I can't remember the number 8. Okay, this one, when you have D divide A and D divide B, you're gonna have, okay, by theorem 2.3.1, property number 8, you're gonna have D equal to A. Okay, sorry, D divide, not equal. D divide A times, okay, let me use variable. Let's use Z1 plus BZ2 for every integers Z1 and Z2. Okay, what can we do next? The next thing we have to do is to try to plug in this term. And we know that J and xj plus k are integers. So since J, xj plus k are integers, so what can we have next? We gotta have D divide AJ plus B. Z2 is now xj plus k. Okay, xj plus k, and this term is h, right? This term right here is h, and hence d divide h. Okay, right now we have d divide h. The next thing we have to do is to have h divide d. So we start from this one here, the greatest common divisor of okay, let me get started. So since h equal to the greatest common divisor of a plus bx and b, so what do we have next? We're gonna use property. Okay, property of divisibility. Sorry, we're gonna use, so we're gonna have h divide a and a plus bx. Okay, I'm terribly sorry. A plus bx. So h divide a plus bx and h divide b. Okay, what can we do next? So since I want to have h divide bx, fortunately we have h divide b. So it's obvious that once we have h divide b, we will have h divide bx. Okay, so since h divide bx and h divide a plus bx, h will divide a. Okay, h divide a by theorem 2.3.1 property number 5. Okay, this is HA, right? And then what do we have? We have h divide both a and b. So now this is what we have. So since h divide a and h divide b, what we have right here, we have the division. We have h divide both a and b, so we need to use divisibility properties. Okay, so theorem 2.3.1 property number 8. What does it imply? It implies that h divide a, okay, let me use variable t1 plus b t2 for every integers t1 t2. Okay, then what do we have next? So since okay, give me a second. Okay, where is it? We have this u here, and since u and v are integers, because we want to show that this term is d, right? And t1 and t2 are any integer. That means that we can plug in u and v into here and here, t1 and t2 respectively. So what do we have? So we're gonna have h divide au plus bv. Okay, and hence h divide d, because this term right here is now d. All right, so we have h divide d. So since we have d divide h and h divide d, what do we have? We're gonna have d equal to h. Okay, so therefore, what do we have? We're gonna have the greatest common divisor of a and b equal to a plus bx b, which is the greatest common divisor of a plus bx and b. Okay, so once we have shown this one and this one, what do we have? Hence the greatest common divisor of AB equal to the greatest common divisor of A, B plus AX equal to the greatest common divisor of A plus BX and B. Alright, so we have proved theorem 2.4.6 already, which state that the greatest common divisor of A and B equal to the greatest common divisor of A, B plus AX equal to the greatest common divisor of A plus BX and B. Okay? And that's it for this video.